Chapter 5. Oscillations. Exercises pages 129 to 130. Exercises Q1.1, page 129. Choose the correct option. A particle performs linear SHM starting from the mean position. Its amplitude as a and time period is t at the instance when its speed is half the maximum speed, its displacement x is. Solution. Exercises Q1.2, page 129. Choose the correct option. A body of mass 1 kg is performing linear SHM. Its displacement x cm at t second is given by x equals 6 sin. Solution. 18J. Exercises Q1.3, page 129. Choose the correct option. The length of seconds pendulum on the surface of Earth is nearly 1 meter. Its length on the surface of Moon should be given. Acceleration due to gravity g on Moon is 1/6 of that on the Earth's surface. Solution. Exercises Q1.4, page 129. Choose the correct option. Two identical springs of constant K are connected, first in series and then in parallel. A metal block of mass m is suspended from their combination. The ratio of their frequencies of vertical oscillations will be in a ratio 1. 1. 4 2. 1. 2 3. 2. 1 4. 4. 1. Solution. 1. 2. Exercises Q1.5, page 129. Choose the correct option. The graph shows variation of displacement of a particle performing SHM with time t. Which of the following statements is correct from the graph? Solution. Exercises Q2.1, page 129. Define linear simple harmonic motion. Solution. Linear simple harmonic motion SHM is defined as the linear periodic motion of a body, in which the restoring force, or acceleration, is always directed towards the mean position and its magnitude is directly proportional to the displacement from the mean position. Exercises Q2.2, page 129. Answer in brief. Using differential equations of linear SHM, obtain the expression for a velocity in SHM, b acceleration in SHM. Solution. The general expression for the displacement of a particle in SHM at time t is x equals a sin omega t plus x. 1. Where a is the amplitude, omega is a constant in a particular case, and x is the initial phase. The velocity of the particle is. Equation 3 gives the acceleration as a function of x. The minus sign shows that the direction of the acceleration is opposite to that of the displacement. Exercises Q2.3, page 129. Answer in brief. Obtain the expression for the period of a simple pendulum performing SHM. Solution. Let m is mass of the bob. L is the length of massless string. A free body diagram to the forces acting on the bob, theta minus angle made by the string with the vertical. T is tension along the string, g is the acceleration due to gravity. Radial acceleration equals omega squared L. Net radial force equals T minus mg cos theta. Tangential acceleration is provided by mg sin theta. Torques. Tau equals minus L mg sin theta. According to Newton's law of rotational motion, tau equals I alpha, where I is the moment of inertia alpha minus angular acceleration. Therefore I alpha equals minus mg sin theta L. If theta is very small, then sin theta approximately equals theta. So I alpha equals minus mg theta L equals minus mg L theta. We know it will follow simple harmonic motion when alpha equals minus omega 2 theta. So I minus omega 2 theta equals minus mg L theta. Moment of inertia I equals ml squared. Here it is clear that the time period of a simple pendulum is directly proportional to the square root of the length of the pendulum and inversely proportional to the square root of acceleration due to gravity. Exercises Q2.4, page 129. Answer in brief. State the law of simple pendulum. Solution. Exercises Q2.5, page 129. Answer in brief. Prove that under certain conditions a magnet vibrating in a uniform magnetic field performs angular SHM. Solution. Consider a bar magnet of the magnetic moment μ, suspended horizontally by a light twistless fiber in a region where the horizontal component of the Earth's magnetic field is B. The bar magnet is free to rotate in a horizontal plane. It comes to rest in approximately the north-south direction, along with B if it is rotated in the horizontal plane by a small displacement theta from its rest position, theta equals O, the suspension fiber is twisted. When the magnet is released, it oscillates about the rest position in angular or torsional oscillation. The bar magnet experiences a torque T due to field B. This tends to restore it to its original orientation parallel to B for small theta. This restoring torque is gamma equals mu B theta. 1. Where the minus sign indicates that the torque is opposite in direction to the angular displacement E. Equation 1 shows that the torque, and hence the angular acceleration, is directly proportional to the magnitude of the angular displacement but opposite in direction. Hence, for small angular displacement, the oscillations of the bar magnet in a uniform magnetic field are simple harmonic. Exercises Q3, page 129. Answer in brief. Obtain the expression for the period of a magnet vibrating in a uniform magnetic field and performing SHM. Solution. Time period of an oscillation body about a fixed point can be defined as the time taken by the body to complete one vibration around that particular point is called time period. Exercises Q4, page 129. Show that SHM is a projection of UCM on any diameter. Solution. Linear SHM is defined as the linear periodic motion of a body, in which the restoring force, or acceleration, is always directed towards the mean position and its magnitude is directly proportional to the displacement from the mean position. There is basic relation between SHM and UCM that is very useful in understanding SHM. For an object performing UCM, the projection of its motion along any diameter of its path executes SHM. Consider particle P is moving along the circumference of circle of radius A with constant angular speed of omega in anticlockwise direction as shown in figure. Particle P along circumference of circle has its projection particle on diameter AB at point M. Particle P is called reference particle and the circle on which it moves, its projection moves back and forth along the horizontal diameter, AB. The x component of the displacement of P is always same as displacement of M. The x component of the velocity of P is always same as velocity of M and the x component of the acceleration of M. Suppose that particle P starts from initial position with initial phase alpha angle between radius op and the x axis at the time t equals O. In time t the angle between op and x axis is omega t plus alpha, as particle P moving with constant angular velocity omega as shown in figure. It shows that acceleration of particle m is directly proportional to its displacement and its direction is opposite to that of displacement. Thus particle m performs simple harmonic motion but m is projection of particle performing UCM, hence SHM is projection of UCM along a diameter of circle. Exercises Q5, page 129. Draw graphs of displacement, velocity, and acceleration against phase angle, for a particle performing linear SHM from A, the mean position, B, the positive extreme position. Deduce your conclusions from the graph. Solution. Consider a particle performing SHM, with amplitude A and period t equals 2 pi omega starting from the mean position towards the positive extreme position where W is the angular frequency. Its displacement from the mean position x, velocity v, and acceleration a at any instant r. As the initial phase x equals 0. Using these expressions, the values of x, v, and a at the end of every quarter of a period, starting from t equals 0, are tabulated below. Using the values in the table we can plot graphs of displacement, velocity, and acceleration with time. Graphs of displacement, velocity, and acceleration with time for a particle in SHM starting from the mean position. Exercises Q6 page 129. Deduce the expressions for the kinetic energy and potential energy of a particle executing SHM, hence obtain the expression for the total energy of a particle performing SHM and show that the total energy is conserved. State the factors on which total energy depends. Solution. Consider a particle of mass m performing linear SHM with amplitude of the restoring force acting on the particle is F equals minus kx, where k is the force constant and x is the displacement of the particle from its mean position. 1. Kinetic energy. At distance x from the mean position, the velocity is. If the phase of the particle at an instant t is theta equals omega t plus x, where a is the initial phase, its velocity at that instant is v equals omega cos omega t plus x. And its k at that instant is 2. Potential energy. Consider a particle of mass m, performing a linear SHM along the path mn about the mean position O at a given instant. Let the particle be at p, at a distance x from O. Potential energy of a particle in SHM. The corresponding work done by the external agent will be dW equals F dx equals kx dx. This work done is stored in the form of potential energy. The potential energy Pe of the particle when its displacement from the mean position is x can be found by integrating the above expression from 0 to x. 3. Total energy. The total energy of the particle is equal to the sum of its potential energy and kinetic energy. From EQs 1 and 2, total energy is. As m is constant, and w and r constants of the motion, the total energy of the particle remains constant, or it's conserved. Exercises Q7 page 129. Answer in brief. Derive an expression for the period of motion of a simple pendulum. On which factors does it depend? Solution. A. Consider a simple pendulum of mass m and length L. L equals L plus R, where L equals length of string, R equals radius of bob. B. Let O be the initial position of pendulum and OB, its instantaneous position when the string makes an angle theta with the vertical. In the displaced position, two forces are acting on the bob. Gravitational force weight mg, in a downward direction. Tension T, in the string. C. Weight mg, can be resolved into two rectangular components. Radial component mg cos theta along OB and tangential component mg sin theta perpendicular to OB and directed towards mean position. D. mg cos theta is balanced by tension T, in the string, while mg sin theta provides restoring force. Therefore F equals minus mg sin theta, where a negative sign shows that force and angular displacement are oppositely directed. Hence, restoring force is proportional to sin theta instead of theta. So, the resulting motion is not SHM. If theta is very small, then. Exercises Q8 page 129. At what distance from the mean position is the speed of a particle performing SHM? Half its maximum speed. Given the path length of SHM equals 10 centimeters. Solution. Exercises Q9 page 130. In SI units, the differential equation of an SHM is d2x dt2 equals minus 36x. Find its frequency and period. Solution. Exercises Q10 page 130. A needle of a sewing machine moves along a path of amplitude 4 centimeters with a frequency of 5 Hz. Find its acceleration 1/30 s after it has crossed the mean position. Solution. Exercises Q11 page 130. Potential energy of a particle performing linear SHM is 0.1 pi 2x2 joule. If the mass of the particle is 20 grams, find the frequency of SHM. Solution. Exercises Q12 page 130. The total energy of a body of mass 2 kg performing SHM is 40 J. Find its speed while crossing the center of the path. Solution. Given mass equals m equals 2 kg, energy equals E equals 40 J. The speed of the body while crossing the center of the path mean position is Vmax, and the total energy is entirely kinetic energy. Exercises Q13, page 130. A simple pendulum performs SHM of period 4 seconds. How much time after crossing the mean position will the displacement of the bob be 1/3 of its amplitude? Solution. Exercises Q14, page 130. A simple pendulum of length 100 cm performs SHM. Find the restoring force acting on its bob of mass 50 grams when the displacement from the mean position is 3 cm. Solution. Exercises Q15, page 130. Find the change in length of a second's pendulum if the acceleration due to gravity at the place changes from 9.75 meters per square second to 9.8 meters per square second. Solution. Therefore, the length of the second's pendulum must be increased from 0.9876 meters to 0.9927 meters, i.e., by 0.0051 meters. Exercises Q16, page 130. At what distance from the mean position is the kinetic energy of a particle performing SHM of amplitude 8 cm, 3 times its potential energy? Solution. Exercises Q17, page 130. A particle performing linear SHM of period 2 pi seconds about the mean position O is observed to have a speed of b²√3 meters per second, when at a distance b meter from O. If the particle is moving away from O at that instant, find the time required by the particle to travel a further distance b. Solution. Exercises Q18, page 130. The period of oscillation of a body of mass m1 suspended from a light spring is t. When a body of mass m2 is tied to the first body and the system is made to oscillate, the period is 2t. Compare the masses m1 and m2. Solution. Exercises Q19, page 130. Answer in brief. The displacement of an oscillating particle is given by x equals a sin omega t plus b cos omega t, where a, b and omega are constants. Prove that the particle performs a linear SHM with amplitude a equals. Solution. Since the acceleration of particles is directly proportional to displacement and directed towards mean position, therefore type motion is simple harmonic motion. Now, let amplitude A equals r sin phi 2 and b equals r cos phi 3. Substituting a and b and 1, we get y equals r sin phi cos omega t plus r cos phi sin omega t equals r cos omega t sin phi plus sin omega t cos phi equals r sin omega t plus phi. Squaring 2 and 3 and adding, we have exercises Q20, page 132. Parallel SHMs represented by cm are superposed on a particle. Determine the amplitude and epoch of the resultant SHM. Solution. Given 2 parallel SHMs represented by cm are superposed on a particle. To find the amplitude and epoch of the resultant SHM using superposition principle, amplitude of resultant is given by exercises Q21, page 130. A 20 cm wide thin circular disc of mass 200 grams is suspended to rigid support from a thin metallic string. By holding the rim of the disc, the string is twisted through 60 degrees and released. It now performs angular oscillations of period 1 second. Calculate the maximum restoring torque generated in the string under undamped conditions. Pi 3 approximately equals 31. Solution. Exercises Q22, page 130. Find the number of oscillations performed per minute by a magnet as vibrating in the plane of a uniform field of 1.6 times 10 to 5 Weber per square meter. The magnet has a moment of inertia 3 times 10 to 6 kg per square meter and magnetic moment 3 am2. Solution. Exercises Q23, page 130. A wooden block of mass m is kept on a piston that can perform vertical vibrations of adjustable frequency and amplitude. During vibrations, we don't want the block to leave the contact with the piston. How much maximum frequency is possible if the amplitude of vibrations is restricted to 25 centimeters? In this case, how much is the energy per unit mass of the block? G approximately equals pi 2 approximately equals 10 meters per second minus 2. Solution. Data. A equals 0.25 meters, G equals pi 2 equals 10 meters S2. During vertical oscillations, the acceleration is maximum at the turning points at the top and bottom. The block will just lose contact with the piston when its apparent weight is 0 at the top, i.e.,